here, too bad we have such a small crowd. This is going to be a good, I hope this is going to be good. The 4 o'clock class fell through the lecture, and everybody's gone, but except the Marines, the few, the proud, the Marines. We're here, right? Okay. This was a weld I went to a place in Montana last year. I bought into and invested into this water well, and this was their high pressure injection line. And when I saw that, I about went bananas. And why would you not want to do that? Gee, purse. I wonder what the joint looked like. You're all welding instructors. Now, let's see here. What's wrong with that one? Droid. Huh? This is a 3-inch nipple going into a 4-inch 45-degree elbow welded onto a 3-inch collar. What a nice job. Anyway, I try to throw a few of these good ones in. My name is Larry ZIRKER. Been an old, I worked 5 years in the oil field as a pipe welder. Used to wear my funky little hat. You know, the people just don't know how to wear these hats right. You know, I gave a few of them away, and the first thing they do is they do this to them. I said, no, you wear them poofy like this. And they said, why? I said, well then, because in Wyoming, it's always either cold or snowing. Then you can pull it down over your ears and weld on the pipe, and then it's poofy so you can protect both ears. So if somebody answers the correct answers today, I got a hat here for you. It's custom made, old school design, reversible and everything. So anyway, retired welding engineer, 30 years with the Department of Energy, welded nuclear fuel rods. That's why I have a radiant face. But worked on airplanes, did a lot of things, lectured, been taught a couple of universities, and now I just lecture. I've been doing this. How many here have been to my lecture before? You were last year, you were last year, but you weren't here, and he's been to about 5 of mine, I think. And you were last year. I ran into another guy that was at mine last year here, and or 2 years ago. And so, were you here? Yeah, I remember you too. Was it any good? Yes. You don't remember? You were the one asleep in the back. Okay.
I was in the back.
All right. Well.
Retired Army. I don't know.
Okay. Well, this is what the story is. I've been wanting to do this since 1975. When I was a young graduate student teaching the welding at Arizona State University, the metallurgy professor came and said, hey, we got a wrongful death. Would you come look at the accident with me? And I said, sure. And we went out to a holding yard, and there was a lowboy that had failed with a D9 cat on it. And when I went out and looked at the welds that failed, I wasn't that good a welder 30 years ago. I'm probably not yet now, but I've got a master's degree at Ohio State and done all this stuff, so I should know something. If you have to ask me a question, ask me real slow, okay? But we looked at it, and you could see that the repair on the weld, they'd run about a 2-inch wide 60-10 big Wyoming weave pass right over the top of it. It was beautiful. It had a nice little, it was about that long, and it had failed, and you could see that they didn't even brush the paint off of the weld underneath, because you could, well, at least it didn't look like the paint had been brushed off, and they welded right over the crack and a big weave. And so it failed, killed the driver. He used the wrong rod, no crack, no fish plates. And I've always wanted to tell this story because I can see a teacher like you teaching a young man how to weld. He goes on to a shop, and the foreman says, hey, Joe, get some 60-10 rod and go out and fix the crack in the lowboy. And what I'm going to do today is to try to give you everything I got here you can have. I have it, you can download it from my website, I'll give it to you, but I got slides and backup material. that you can give a couple hours of lecture on it and train your people that when you go out and do something like a lowboy that you know has different material, but they just tell you to go out and do it. Maybe you can stop somebody from getting hurt. And so let's get on with it. So the objectives is to help someone avoid accident, to provide you lesson material. Have you ever used my stuff in your class from last year?
No.
Oh, the other guy did. But that's all right. That's your problem. No. That's maybe you might use some of this. He liked some of this stuff. And I'm going to show you how to weld it and to repair A514, which is the same as T1. We've all heard of T1, but you may not have ever heard of 514. And show you the methodology of how I did a demonstration test with a best practice and a bad weld, bad practice, best practice, and show you the metallurgical and destructive analysis. Boy, you're gonna love this. And then I'll give you all the slides. Okay. For a hat today, if anybody can answer those 5 questions, I will give you a customized hat. Let's see. You want to take a shot at it? Anybody have an idea?
You need hydrogen rod, don't you?
Yeah, well, okay. Which one do I use? There's probably 10 of them, isn't there? Or 5?
7018?
Okay. Wrong. That's all right. Yeah.
8018?
No. Okay.
Just as wrong.
Just as wrong.
But higher tensile strength.
Yes. Okay. We got a lot of slides to go through, so let's do I'll do the answers. Oh, when did I do the answers? Okay. You got to match the base metal.
110, wow.
This is T1. This is 110, 120,000 tensile strength material. It's got to be heated to drive off the moisture. It's got to be, you got to have heated rods. You got to free of moisture. You got to be low hydrogen rod. Depending on the thickness, depends on the heat. You got to totally remove the crack, because cracks will grow, and you've got to use a string of beads and no more than less than 2 inches wide, 2T wide weave. And when you fish plate, the fish plate should be 2 times as long as the height. Yes?
On your fish plate, I have a question on that because I've done trailer repair. And I put them in a triangle
That's exactly right.
type method. Is that correct?
That's correct.
Okay.
What kind of welding rod do you use to weld the 836 fish plate on this high tensile steel with?
What did I use?
What should we? Now, you're welding this onto a high tensile strength frame. What kind of rod should you use? Wrong. If you put the high tensile rod onto this 836, it'll break out the weld. You use 7018. You match the welding rod to the lowest tensile strength of the steel. I set you up, but I wanted to do that. So let's go back.
So that would be a 1020 plate?
It'd be like 836, 1020.
Okay, 1020.
Yeah, 836. So what kind of SMEW rod you'd use? 7018. Okay. Why? Because you match the strength of the metal. What is T1? It's a high strength, low alloy steel, 120 KSI. If it's thicker, it'll be 110. It's commonly called T1. It's a quench and tempered steel. Quench and, yes?
How would you know that that's what the base material is? Call the manufacturer before you try to repair it?
Well,
How do you identify?
sometimes you can see it written on there.
Okay.
But the prime thing is, there'll be a big sign there. It'll say, "Do not weld on this frame,
Yeah.
dummy." Well, then you know it's T1, because it's not that it was built by welders, but they didn't want an unknowledgeable person doing it. generally a low boy, because it's the same weight as 836 steel. It's the same weight, but it's 2 to 3 times stronger, and they tax you on the trailer is taxed on how much it weighs. And it's calling a D9 cat that weighs 100,000 pounds. So if you made a frame out of 836, it'd weigh 100,000 pounds to haul a dozer. And this is steel on steroids. It's weldable, and I'm going to teach you how to do it today. 3 important, here it is. You got to use the right rod, and you got to use the right preheat and interpass temperature, and you got to have the right joint preparation, right welding technique, and a reinforcing plate to fix it. If it cracked without a reinforcing plate, something's wrong with the design. So you fix it, put it back original, put a plate on it, and then you won't crack again. Heat affected zone cracking. What's another name for that? Underbead, very good. Hydrogen cracking. There's dang, I got my notes there. There's several. Anything with hydrogen, underbead. 3 things must happen to have underbead or hydrogen cracking. You got to have hydrogen in it. You got to have a sensitive material. You got to have martensite. You can't get this with 836 material. The stuff you practice welding on with your students, you could probably weld it and throw it in a snowbank and it'd probably still bend just fine. But this stuff is like, consider, I had 2 girlfriends once. One said, I'll make you cookies. I said, okay. And she made me sugar cookies. Egg, flour, cooked them with a little bit of sugar on it. My other one, my wife, she said, I'll make you cookies. And she made it with oatmeal, raisins, chocolate chips, coconut, and pecans. Well, that's the kind, they're both cookies. 836, 514, both steels, but this one here's got steroids, and it's got a lot of goodies in it. And you eliminate any one of these 3, and you don't have hydrogen cracking, generally. That's why we do what?
Bake the electrodes.
We bake the electrodes. We get rid of the hydrogen. Very good. You guys are good. All right, here's something. If you read the book on welding this material, it'll say, I copied this right out of a book. 1/2-inch material, preheated to 350, interpass temperature 350, and you can't have a heat input of more than 47 kilojoules per inch. You know, and that's and so here's the formula for it: volts times amps times second over 1,000, and times the travel speed. Well, when I did that, it came up to 60 kilojoules. How do I fix that problem? How do I weld it now? My kilojoules are way too high. I got too much heat input. I do what with my travel speed? You increase it. Will that drop my kilojoules? Yeah. Good question. Good answer. Also, what else can you do? Yeah.
Smaller diameter electrode.
Turn your amps down, and that would get you right down to the 47. This is something you can do with your classes. You give them this, and they should know how to multiply something simple like. Even those, my 2 friends there, they're from Utah. Their guys should be able to do that. Do they teach algebra in Utah?
I think so.
They do.
You can shorten your arc too.
Okay. See, you taught me something. More details. Okay. Now, this material is quench and tempered. That means when it's made in a factory, and they pour it out, and you get that sparks, and they make these big long ingots, and they're all right red, and when they get to this, they run it down through, and they get it to the right temperature, they squirt water on it. And so if I take 4140 steel, what they make gun barrels out of, they get them in the untempered, unhardened condition, and they make the gun barrel and make the riflings, and then they temper them so they're real hard. Well, you couldn't machine them if they were hard, right? So but they fool this material and they quench it because quenching makes it harder, and harder makes it stronger. And then they temper it a little bit. It's like having tempered glass. That if you hit it, it doesn't shatter. It doesn't. And so what you got to do? This is the secret right here. You got to have enough preheat to drive off the moisture, and just enough preheat not to. If you have a thicker A36 steel, you want a lot of preheat because that slows the what? Cooling rate. That reduces the hardness. This stuff, you want to match the hardness, so you want it to quench a little, the weld to quench, and that's why you don't do a big weave. If you have a stringer beads, it quenches and makes the hardness closer to the base metal. And I'll show you an example. So you got to have just enough, and you got to have, but you can't have it too low. You got to have enough preheat, and you can't have it too low or too fast, because then it gets too hard. And then if it cools too slowly it becomes softer, weaker, less tough, big grain growth. You have too much. And also the code says that you have to wait 48 hours. Why? Pardon me?
Make sure that the hydrant's out.
So there's no cracking. That's exactly right. That's right in the code book. And so, okay, it's very sensitive. It's kind of like getting married to a redhead. If everything's right, everything's cool. But you screw up a little bit, it's hell to pay. They blow off. This is this material. You got to have. Now, this is something that most students don't understand. You have to have a minimum preheat. If the preheat's 75, can I preheat to 100? Yeah, it won't hurt. It's got to be a minimum of 75. But if it's a 200 or 300 degree maximum interpass temperature, if it's 300 maximum interpass, can I have a 200? Yeah. Can I have 400? No. So it's a minimum preheat, a maximum interpass temperature. Most of your students will never know that until they get out. That's something you can tell them. And it's a balance between the time passes and the base metal thickness and preheat. How do you measure temperature on something like this? How do you guys? A what? Oh, that'd work. How's the old school way? Temple stick. If you spit on it, it bounces 3 times before it falls off, that's 300 degrees. No, I'm just kidding you.
4 times 400, right?
Yeah. All right. Where do you find information? If you see some strange, oh, I'm sorry, I keep wanting to move around. I'll just sit right here. He keeps looking at me. So. If you get a piece of metal, 514, have you ever heard of the 514 before? Well, how would you know how to weld 514 if you didn't know how to weld it? Where would you go? Look it up somewhere. Where? Code is the very best place to go. It will tell you the welding rod. And then it always tells you the mechanicals and the chemicals. Now, if you can find the chemicals, what's another really good way to give you a feel for this material? That's your students are blessed because they have a bright guy. If you quickly do a calculation of carbon equivalent, and what do you think the carbon equivalent on this material is? I think it's 0.68. What does that tell you instantly? Mr. Army man? Mr. Marine? What does that tell you? 0.68. That should be a red flag saying, wait a minute. What did you say?
0.68?
Yeah, 0.68. When do you start to preheat when you weld? What carbon equivalent? You guys?
0.5.
Oh, heavens no, 0.3. 0.3 something, you start worrying about it.
I threw a guess out there. Trying to
Well-
get my buddies off the hook.
I know.
They sunk us all.
Yeah, well. Were you a Marine or did you just wear a hat? Huh? Well, then I'll speak slower then next time, okay?
Will that hurt?
I'll do them block letters, okay? I had great friends who were Marines. I'm sorry. What you can do, you can go to code books, the WPS. If you have a regular company and they'd have a WPS, they'd tell you how to do it. But sales rep may know, web search may know. You can go to apps. Apps are really neat. Did anybody come to Bob's apps lecture? That was sweet, wasn't it? Yeah. Okay, this is what I did. What am I looking for time?
Over half an hour.
Oh, well, we can fill that. Didn't mean to babble so much. All right, what I did is I thought, okay, to do this right, I need to do a practice test. And so I went out and I bought some of this steel. Oh my gosh, that was pricey. It cost me $130. And then I bought some welding rod. Ooh, this is really expensive. And then having them cut, the samples cut, that was $30 a coupon. It was water jet. It was the best way to get them. It didn't come out with a plasma torch or a laser. It was water jet. So I welded one up correctly. Right heat input, welding technique, correct practice, right rod. The other one, I welded up like a young kid that didn't know any better. He was sent out to weld it. He'd probably take a 60-10 rod to fill up the cracks and some 70-18 to weld it. That's exactly what I did. So I duplicated it, and I tried to make a duplication of welding a frame where I had a back weld on one side and welded it all from the other side. And there I am with my shirt tail unplugged. And you're not a welder unless you got a Lincoln. And there I got my coupon in my hand. And okay, here's a safety share. You got to have a safety share. The person who can first tell me what's wrong, I will give them this. Yes?
There's no guard on your grinder.
That's a sanding disc. That's allowed.
Ear protection?
I got ear protection. It's right behind my collar. You can see it's my little...
No gloves.
Right on. Do you like peanut butter or do you want other? Sorry, I didn't throw that very good.
Sure.
You want to trade?
Trade, yeah.
Oh, well,
Thank
good enough. Okay, that's right. I didn't have gloves on. I was sanding down my disc. Okay, there's my plates. I did a 836 plate so I could practice weld. I don't weld enough. I practiced on that one. Then I'd run it on the 836, and then I'd run it on my good one. This is the bevel I used, and then I'd flame cut the bad one. Now, we're putting so much heat into it that quench and tempered, it's like taking your pocket knife and putting it in a campfire and leaving it for an hour because it's tempered, and you put the heat into it, and you're going to mess it up. You're going to anneal it. Well, that's what happens. You flame cut this material, that's what happens. Plasma cut's okay. Flame cut's bad. So the other one I flame cut the joint. Here I tacked it up. Here oh, look there's my temple stick. Where'd I put it? Oh, always right here. There's my temple stick, and see it smoking? I got the right temperature. And I preheated, the good one I welded at 300 F, and the bad practice, 600 F. And once I got going, it was hard I had to wait 20 minutes to cool that other one down. It would take 20 minutes to cool down. I kept wanting to squirt it with water, and I just didn't think I should do that. There's the back weld. There's the first fill pass on the back side, second fill pass. Then I cut out these coupons out of each one of them with the water jet. And and we'll show you those. There's the side bend one, best practice. Didn't even bend this hard. Look at it, snapped it. The best practice, look at the tensile strength. 128K. Isn't that sweet? 116. And they both broke outside of the fusion. Elongation. I had this welding joining manufacturing group out of Denver do my testing there. Just such a good old guy. We went to school together. The bad practice, look at the elongation. It's not that it didn't elongate, it fractured before it could stretch. I was even surprised welding it with 7018, it still broke at 97K. There's the base metal, just a raw base metal salt, no weld, base metal tensile specimen. Heck, we had a higher tensile than the one we welded. Did a little elongation. Hardness profile. Oh, this was really interesting. I used to work for the Idaho National Laboratory. That's the nuclear arm of the Department of Energy. And remember, they did a grant for me. I asked them, nobody in town can do it, and they said, well, we'll do it for you. And I had to get somebody to give me 4 hours of billable hours. And hardness is directly related to strength. It's a direct relation to strength. The good weld, this is really good here. Now, the weld shaped like this. Well, the hardness traverse was right through the center, 1/4 inch down from the top. And you notice that this is the base metal hardnesses, and they were a millimeter apart. And there was about 18 of them, I think. So this was the center of the weld, right here. This is the base metal. The base metal got a little dip for the heat effector zone, and then the weld metal was the same hardness as the base metal. That's what it got quenched just fast enough to cool, to harden a little bit, but it wasn't too hot to anneal the material. That is the secret. Now, the bad weld really had a dip. There's base metal. It had a real dip here, come up, had a little spike for some reason, and then the weld metal was really low and up, and then it hit a spike on the heat effector zone. Now, we'll show you why this happened here in a minute. Put them, superimpose them. Heat effector zone is right here. 200 Vickers hardness is equivalent to an 83,000 PSI material. Still pretty good strong, but when we're dealing 120, that's 40,000 pounds of difference. That's a big delta. 300 Vickers hardness is equal to 100,000 tensile strength steel. Now, oh, I brought my sample. You guys will like this. You can look at it. If you'd like to pass it around, just don't touch it with your fingers, or my buddy will dislocate your shoulder over there. And then there's something really neat that nobody will notice, but you look at it for a second. All right, there it is, right? It was taken, the hardness test was taken right to the center, just like that. Now notice, see the heat effector zone here? Nice even heat effector zone. See the heat effector zone here? It's about twice the width of that. Well, I had twice the heat input. Big weld. And you can see how big and gobby this weld was. It put a 6010 root in it and had to grind it down, and big weave passes. Now, I ground off the weld and got it ready to be cut into the coupons, and I noticed some porosity. And I noticed a little, and so what I did is I did a repair weld. Can you see the repair weld right there? Can you see the repair weld right there? And there's another one right there. It's a different color. And when you hold it in your hand, you can see it better. And that's so, the metallurgy doesn't lie. The microstructure busted me. A good guy would have said, hey, you had a repair weld there. I'd have gone, huh? How'd you know that? Well, you can tell. And that's something to think about. That even if you, this is what you can do with your kids. They give you their test coupon, and it's got a little grind mark on the side. We'll polish it up and get some nitrile, and you'll say, well, what's this grind mark here? Oh, I don't know. Well, he had an arc strike. Then you polish it up, put some of this acid on, and it'll show up just like that, and you say, you got busted. I'm sorry. You arc struck. That's a serious no-no. Out. Don't you guys deduct points if they make arc strikes on their coupons? Sure. Yeah, the guys at Idaho State, it's an automatic. It's gone. It's a 50% right off the bat. And so, but anyway, I just thought I'd share that a little bit with you. All right, this is something that is really awesome. Now we're going to. Okay, I got another bag of peanuts here. Oh, thank you. Now, this is the base metal down here. This is what the microstructure of the base metal looks like. What's this called right here? That's weld metal. That's weld metal. A weld, these columnar grains. If you were to look at them closely, they should be martensite. But this is a 50X. If you were to see it at 200X, it would probably show up as martensite. However, this is something interesting. When the weld metal melts onto the base metal, which is right here, there's your fusion line right there, it always grabs onto an existing grain, and it says, oh, I like to grow in that grain preferential grain growth. And that's why these will always, they'll always be attached. If you look real careful, they're always attached. For some reason, this one attached down here, and they attach onto a non-melted grain, and they grow. And they usually grow to the heat. Usually, they always curve to the heat source. This is right close to the top, and you don't see it. Now, how hot, if I were to come out here an inch or so, how hot would that be? Or 3 inches? How hot would the base metal be 6 inches away from that weld? Give me a guess.
Whatever your preheat.
Yeah, 100, whatever, or room temperature if it was.
Depends if it's a good practice or bad.
Yeah, that's your preheat temperature. So what temperature does it start the grain growth? When does the grain growth? If you can give me about what temperature does the grain growth happen? Huh? That's exactly right, 1,300 degrees. Why is that the right temperature?
That's when it started to change phase.
Very good. It starts to.
See, you were teaching me back there.
Yeah, I know. I cheated.
Smart.
Yeah, I cheated. But okay, that's right. So from about right here to right there is about 1,300 degrees, and this is your austenite region. This is all non-magnetic from about right here. And if you ever do that, you can heat up a piece of steel. I told some of you this. Heat up a piece of steel on a magnet, and when it drops, it's reached 1,333 degrees, which is a Curie point, which is non-magnetic point. And you can say, oh, I will show you a phase change. And when it drops, their eyes usually get that big, and then if you really want to do something neat, you drop it, you get some high tensile steel like 4140 and drop the little piece in a bucket and quench it. And then you hit it with center punch, the one you heated and the one you didn't heat, and it'll usually fracture your center punch because it gets so hard. And then you can have a discussion, well, why did this happen? Well, it quenched too fast. How do you stop stuff from getting hard? You preheat stuff. That's why we preheat. All right, now watch this. This is really neat. That's the best practice one. See how small the grains are? When you overheat, the grains grow. I had 600 degree interpass temperature. See how they don't look burnt. See, here's your base metal right here, and here's your, this got up to about 1,300, and here's your grain growth. And now you can see how the columnar grains grow out. This was the last pass right here. This was probably the first fill. Aren't those beautiful pictures? These are all in the download. You can have these, show them to your class. This is what happens if you overheat. The grains get big. Big grains are not as tough. Big grains are not good. But with 836 stuff, probably would never make any difference. Pour the heat to it, it welds nice. It's not enough tensile strength to make a big difference. But this kind of stuff, it's like that redhead. You don't do it right, it's hell to pay. And now, I've seen this. I stole this out of a magazine. Out of a textbook that I had when I was at Ohio State. And phase diagrams are always vertical, and these are always horizontal. And so I thought, it hit me in the middle of the night. I said, I know what to do with this. I turned this bad boy on its edge. And here we go. This is all, everything you guys weld, probably 99% of your materials is going to be perlite and ferrite. It's going to look just like this. A little perlite, carbon's out here. What's the percentage of carbon in those things? For a hat, who can tell me what percentage of carbon is those perlites?
18.
Okay, this is where, pardon me? 83, that's right. Do you want a hat? You can have that. All right, this is what we're going to do. Just everything you practice on in welding and pipe coupons and plate coupons, it's all going to be here because it's always going to be, it's going to be about 0.2, 0.3% carbon. It's going to be right over about right here. And it's all going to be right here. So it's going to, everything's going to, now this is the iron carbon phase diagram. Well, steel is not an iron carbon phase. It's got manganese in it and a bunch of other stuff. But this is as close as we can come to it. So when you heat it up, and when it gets up to about 1,330, right about there, it changes into this epsilon thing, which is another symbol for gamma, which is another symbol, means austenite. When it gets into that, the carbon that's in the grain boundaries and in these little, it's like chocolate chips. And if you were to heat up chocolate chip ice cream on a stove, it'd end up to be chocolate milk, wouldn't it? Those chocolate chips would dissolve. And steel, when you heat it up, it turns to chocolate milk, but when you cool it slowly, it goes back to chocolate chip ice cream. But when you heat it up, the carbon in here, this is 0.83% carbon, these little nodules, and there's a lot of carbon in the grain boundaries. They will start to dissolve, and they'll be out in this matrix here. I don't know why they have those there. They shouldn't be there. But the carbon dissolves. And what's the biggest hardening element, chemical element, the biggest hardness? Pardon me? No. What chemical element or material contributes the most to hardness of anything? Carbon. Carbon does. Okay? High carbon steel. Drill bits, high carbon steel. And so the carbon is dissolved when it starts to heat up, and it's dispersed in the matrix, and then that's why if you quench it real fast, the carbon's trapped there, and it changes to martensite. Very good. And this point right here is called a what? That's called, okay. If I showed you this up higher, if it's liquid to liquid, it's a eutectic. This is the tectoid, I think, because it's metal, it's solid. And so now what happens is, if you're up here melted, now how big a zone is this going to be in a plate test? If you're doing a plate test, how thick is this region going to be in your actual metal? Probably an 1/8 inch, maybe 3/16. Not going to be very big, because but that's why this is your grain growth, this is your heat effective zone, and this is the base metal, so probably an 1/8 inch, 3/16, depending upon how big you're weaving and how much heat input. As the metal starts to, did somebody have a question? As the metal starts to cool down right here, it'll start to change into your austenite, and these are they call these prior austenite grains, and they get coarser as they get hotter, and that's why they were so hot in that 700, 500, 600 degree heated one. And they cool. They say, we're not going to melt, so they freeze right there. And that's why this is where the hardest part on a weld, if you're welding something that's got a little alloy in it, that's why this is the hardest, because it's cooled the fastest. Okay? And if you had a little heat input, preheat to it, a little more heat input, it wouldn't cool as fast, and your microstructure would be what? Your heat effective zone would be softer or harder? Softer, little preheat. Okay. Now, as it cools down through here, this is kind of a neat thing to think about. You've never, I would believe that none of you have ever been taught this before. But what happens is when it comes down here and your little particle hits this line, it says, oh, I'm going to plate off, this is a ferrite little phase out here. That ferrite wants to plate over there, and it's going to start freezing sooner. So now, if I deplete myself in ferrite, now my austenite, I'm more austenite rich, and so it comes out this way a little ways until it drops some more temperature, and then it comes down and it says, oh, I hit this line here. I'm going to plate out some ferrite. Oh, now I'm austenite rich. And it comes down like this, and it stops when it gets right there. You're solidified. And it automatically changes in the perlite and ferrite. Now, that's why arc strikes are so hard. It's because the carbon content is higher of that little speck of weld metal. That makes sense? There, now you can tell your students this and you explain to them why arc strikes are so bad. There's a couple of samples of fish plates. They always like that shape because the stresses, where's your stresses? Where's the most stresses in this piece of material, in this beam? Yeah. That's where the most stresses are. Okay, let me ask you a question. You ever cut a piece of glass? Have you ever seen it done? Did they cut a hole in the middle? No, they scratched the top surface. The stresses are on the top and bottom. You ever seen a lowboy that had these big fancy 5-axle lowboys, and they'll have big holes cut in the frame? Well, you could probably drill a hole through a tensile test weld specimen, and it'll fracture in the base metal. Stresses go down the top and the bottom. And so that's why, since you put a point there, you'd think, oh, that's a stress point. Well, the stresses are generally up on the top. Generally, you have it a little bit more like that. And if you had it straight up and down right here, then that spot right there would be the stress point, and that's where it gets you. So you put them in a diamond shape. All right, now, you've got a pad. come up and sit right here. Now, and I want you to write some notes down, and we're gonna test you.
I don't know about that.
You can just have a seat right there. I gotta have my brains here. You know, guys, I just don't move very fast anymore. Ugh. This I think, would be a cool way to do a test. And I want you to, I'm going to read this to you. I'm going to read it to everybody, and then you're going to write them down. I wanted a chalkboard, and I forgot to ask them for it. And I'm going to read you this scenario, and I want you to start to write down anything pertinent that you're going to learn from this so you can make the right weld. And then you're going to read them to me, and then we're going to ask you why you didn't do more.
Okay.
Okay? Oh, my phone. Where's my phone? It's ringing. Where's it at? Yeah, there it is. Hi. Oh, is this the famous Bubba with his arc flash welding truck? Yeah, Bubby, this is Buddy, the heavy hauler from Casper, Wyoming. Did you survive the New Year's Eve celebration last night? Oh, okay, I'm glad. Hey, do you still have some of that hippie pipeline rod in one of the boxes of your old 1-ton welding truck? Yeah, 8010 hippie, HYP, that's it. Yeah, the local Department of Transportation inspector caught me the other day. He said I had at the weigh station, they said I had a crack in my gooseneck, and they said it in my 3-axle lowboy, and they told me that it was a high-strength steel frame, and I needed to get it fixed. Would that hippie rod be strong enough? Yeah, okay, that's good. I'm hauling my D9 dozer to Montana in the morning, and I need you to come up to my yard at 8 o'clock in the morning and fix the crack. Just bring your hood and a handful of hippie rod from your truck. Yeah, I'll park it outside, and then we'll just drag our leads out and weld it right out there. Yeah, I'll have the snow removed. I need to leave from Montana by 10 o'clock. That should be more than enough time for you to put that famous Wyoming weave over the top of this crack. You know, that big weave pass you used to do in the oil field? Thanks. We'll see you then. Bye. All right. This would be a neat way to test students, is to read a little thing like this. And then, all right, how do we weld this? Let's see if he picked up anything. There's a lot of things. Okay. Well, let's see. Casper, Wyoming. Anybody know where Casper, Wyoming is? That's the armpit of the world, often the coldest place in the United States. How cold do you think that'll be on New Year's Eve, on New Year's Day? Easy 20 below. Okay, is that a piece of data you picked up on?
Yep.
So what are you going to have to do to this weld?
I need to know what temperature it's at and bring it up to the
You just need to preheat it up.
temperature.
You need to preheat it up to about 200 or 300.
Right.
Okay, that's good. You got that one. Oh, this high-strength pipe, this pipe rod, is that going to work? This hippie rod?
You said 80-10,
Yeah.
not for the high strengths.
No, oh, good. So what kind of rod would you use?
It's a rod that would match the tensile strength of the steel,
What would that be?
like a 120.
Yeah, that's a good idea. That's right, 120/18. Now, where would you have to have that rod? Rod oven. Oh, good. See, and this is a neat way to do a test for students, and you read it to them, and then you bust them really bad. I was going to put you two guys up on chalkboards, but these are guys that I hang around with. So, all right. Is this weld going to be under stress that he's going to repair? How much stress do you think?
D9 stress.
A D9 stress, 100,000 pounds, 100,000 pound load. Would you want to weld on a trailer with a 100,000 pound load? And I don't think so. You'd have to.
I'd let you do it.
Yeah, I'd do it. Should you have it outside, or should you have it put inside?
Inside.
You should have had it inside the night before and let it. It might be warm, but that's for you You should have unloaded the trailer. You unload the tractor. Did you catch that?
Sorry?
Did you catch that? You should unload the trailer?
It would make sense.
Yeah, well, you didn't write it down, though.
I didn't.
Oh, see, we busted him. Okay. How long was he going to wait?
2 hours.
Yeah, how long are you supposed to wait? 48 hours. So, anything else that,
Technique.
what kind of technique?
Wyoming weed.
A Wyoming weave, is that a right technique? No. Was he going to gouge out the crack?
Never say anything about that.
He was going to weld, he said, weld right over the crack. I want to put a Wyoming weave right over the crack, you know, like the one you used to do in Wyoming. So, wrong technique, didn't gouge out. Did you pick up anything of that? Did you get crack removal?
No, I didn't recall you saying anything about that.
Oh, okay, well, you're supposed to, are you married?
Not yet.
Oh, well, when you do, you'll know mind reading better. Okay,
I'm only engaged so far.
well, then
I'm working on it.
then do you know what the 3 rings of marriage are?
Are you telling?
No, the wedding ring, engagement ring, and the suffer ring. You can cut that off. Oh, bad. Okay. Okay, I think we got everything. So, did I tell you this was a good one? Was this okay for you guys?
Yeah.
Now, you go to my homepage, ZIRKER Consulting, and it has downloads. Thank you, I've abused you enough. You're a good sport. And it has downloads there, and you can get the 2 lectures he gave on apps. That one on apps, if you didn't get it, that is a sweet thing to do. And then the weld codes, and you go down and you open it up, and it'll say 5/14/2003 FabTech lecture. And what I'll have in there, it takes a long time to download it. Oh, I guess I deleted it, but I had about 15 supporting websites that have McKay Rod of 11018, 12018, and it talks about everything, and a couple of, and one WPS from a national lab that how to weld it, and a whole bunch of chemicals, ASTM sites. So you'd have some information, and all the slides of the testing, and all the slides of the metallurgy, and all the slides of the making that sample. Any questions? Well, thank you for coming. I hope that was worthwhile.